In this tutorial, we're going to talk about standard scores and why we need them. If I say that I have 17 US dollars, or some object is 17 centimeters long, or the temperature outside is 17 degrees Celsius, it's not that hard to figure out what that number 17 means. But if I say that you scored a 17 on a depression scale, without any additional information, it's tough to figure out what that number 17 means. Now those other measurements, economic value in US dollars, temperature in degrees centigrade, and length in centimeters, have meaning because there's some sort of standard that we can make reference to. With most psychological measurement, there's no absolute standard that we have an intuitive sense of what it means. And so we have to make do with what we have. And what we have, typically, is a mean and a standard deviation. So here's a distribution. Let's say it's the distribution of those depression scores from that questionnaire. In the population, the mean is 23, and the standard deviation is 5.01. So just eyeballing it, a 17 falls about right here on the low end of the depression scale, which would mean that the 17 indicates a score that doesn't indicate depression. Usually depression is when you get a score way up here. So if you score a 17 on a depression scale, that's probably good news. Now these two numbers, 23 and 5.01, let's face it, are difficult to work with. They're kind of ugly numbers. I mean, no disrespect to 23, but it's not a number that we think about very often. And 5.01, if it were 5 exactly, 5 is a great number. Everybody knows how to count by 5s, 5, 10, 15, so forth. But it's 5.01. That is not easy to work with. If all psychological scales had a mean of 23 and a standard deviation of 5.01, well, eventually we'd get used to it, and we'd have a sense of what the numbers would mean. But the sad fact is that all psychological scales have different means and different standard deviations. And that diversity of means and standard deviations makes it difficult to compare numbers across scales. What we need to do is transform these scales so that they have a mean and a standard deviation that we're familiar with and is easy to work with. What we need to do is transform the raw scores are untransformed scores, into standard scores. The mother of all standard scores is the z-score. In fact, when you say I'm standardizing a variable, what you mean is I'm converting these scores, these raw scores, into z-scores. We convert raw scores into z-scores using this formula here. We take each raw score, we subtract the mean of the variable, and then divide by the standard deviation. So if we take the example from the depression scale earlier, we would take each score, subtract 23, and divide by 5.01. It may not look like it, but this formula is surprisingly elegant and informative. What it represents is a ratio of a deviation to a standard deviation. A deviation is a difference, but it's not just any difference, it's a difference from a standard. In this case, it's the observed distance from the mean. The mean is the expected value of this variable. It's the central tendency. It's our best guess in the absence of any information of what any score will be. So this deviation is how far is this score from expectations. So it's a deviation. The standard deviation is the typical distance from the mean. So the deviation all by itself may not be very informative. It's a distance from a mean, but how big are those distances usually? What's the typical distance? Of all the scores in the X distribution, how far are they usually from the mean? That distance is the standard deviation. The standard deviation is the standard to which we compare all deviations. Putting the whole formula together, what a z-score represents is the distance from the mean in standard deviation units. So if I say I have a z-score of 2, that means I am 2 standard deviations above the mean. When we convert raw scores into z-scores, those z-scores have certain properties. The mean of z-scores is always 0. If the distribution is normal, the mean is 0. If the distribution is skewed, it's 0. If it's kurtotic, it's 0. It doesn't matter. Any distribution, once it's been converted into z-scores, the mean is always, always, always 0. And likewise, the variance is always 1. The square root of variance is the standard deviation. The square root of 1 is 1. So the standard deviation of a z-score is also 1. And this is true no matter what kind of distribution you have. Now, Converting raw scores into z-scores makes a lot of things very convenient for statisticians and mathematicians. Z-scores are very easy to work with. Often when we work with complex formulas, we convert everything to z-scores and then we go from there because it makes those formulas a lot easier to read. However, z-scores do have some drawbacks. One is that the mean is 0. And it's kind of weird to think about 0 not meaning the absence of something. When I say I have $0, I mean I have $0. But if I say that my income has a z-score of 0, that doesn't mean I make no money. It means I make the average amount of money. And that's an odd concept to think about. That 0 doesn't mean the absence of something, it means the mean. Another problem with z-scores is that about half of the scores are going to be negative. They're going to be below 0. And for some kinds of measurement, putting a negative number just seems strange. So if I say that my IQ is a -1, that's weird. It means like I have negative intelligence, and that just doesn't feel right to a lot of folks. And so what we do is we transform z-scores so that the mean is a positive number and all of the other numbers are also positive. Another problem with z-scores is that we typically round them to 2 decimals. Now this is just a convention, there's nothing special about 2 decimals, but we often round z-scores to 2 decimals to communicate things. And a lot of folks don't like to deal with decimals. We'd like to deal with integers. And so converting z-scores into a metric such that we can round those scores without doing too much damage to the variable, without distorting it too much, is typically a good thing. But there's another problem with z-scores, is that they often look too precise. Suppose I tell you that an object is 15.97 centimeters long. Let's say this line is 15.97 centimeters long. If I tell you this, you're probably assuming that I'm using some sort of ruler that is accurate to the hundredth place. But if the truth is that I'm using a ruler that looks like this, and wherever the number is, I just round to the nearest line, and that line gives me a number like this, 15.97, then I'm not being accurate. This line is longer than 15.97, and I've given the impression that I've been very, very accurate in measurement, when in fact, my measurement is rather crude. So you're probably thinking I'm using a ruler like this, but unbeknownst to you, I'm using this very crude system of measurement. That is not a good thing. So what would be better is if I converted this number, 15.97, to some system of measurement that conveys the kind of accuracy that I actually have with my ruler. This is another reason that we don't stick with z-scores when we try to communicate our results to the public. We like to convert our scores into a metric or a scale that conveys the kind of accuracy that we actually have. Suppose I have 8 questions on a spelling test or something like that, and I just count up the number of questions that you got right. The very best that I could do with this spelling test is to divide people into 9 categories, 0 right all the way up to 8 right. Now, probably wouldn't look this good in practice, but under optimal conditions, I could slice the distribution up like this. Let's say it's a normal distribution. And these numbers would convey accuracy within a whole standard deviation. That is, if you scored a 4 on the spelling test, your true position is somewhere between -1/2 and +1/2 on the z-score metric. If it just so happens that when I use my formula x minus the mean of x divided by the standard deviation of x, use that z-score formula, it might turn out that 4 is like, 0.2 or something like that on the z-score metric. That 0.2 is, somewhere around here. The truth is that you might be anywhere between here and here, but my number says 0.2, and that conveys a level of precision that I don't actually have with my scale. Now, one thing I could do is just add more items. Let's say I go from 8 items to 16 items. And now, under optimal conditions, I could slice my distribution up into 17 little slices. But even so, my numbers can only convey accuracy up to 1/2 a standard deviation. If I'm rounding my z-score to 2 decimal points, that would mean that I'm slicing each standard deviation into 100 slices. And I don't have that kind of accuracy in my scale. I only have 16 questions. I couldn't possibly get that kind of accuracy. And so what I need to do is change these scores into a metric that's simple, easy, and doesn't convey accuracy that isn't there. The crudest kind of standard score that we use is something called the Stanine. Stanine stands for Standard 9. Once you convert something to a z-score, you can transform it again so that it has a mean of 5 and a standard deviation of 2. I'll show how to do this later. Then we round each score to the nearest integer. Other than the z-score, all of the standard scores that follow, in practice at least, are rounded to the nearest integer. So with Stanines, the mean is 5, and 5 is a number that we're typically comfortable with. And what's nice about this is the range is these counting numbers, 1 through 9, which we're very familiar with. And what's also cool is that each number represents half a standard deviation. So from 4 to 5, we've gone up by half a standard deviation. Now when I say I have a Stanine of 5, I don't mean literally that my z-score is 0. What I mean is that it's somewhere between negative 0.25 and positive 0.25. Where exactly? Not really sure. If I had to guess, it's probably in the middle, but it could be elsewhere. The two exceptions are 1 and 9. The width of this slice and this slice is not a half a standard deviation. It actually goes down all the way to negative infinity, and 9 goes all the way up to positive infinity. Technically, we could have a 0, and we could have a negative 1, and a negative 2, and we could have a 10 and 11, but in practice we don't. We just take anything that turned out to be out here and just round it and transform it and it becomes a 1. For this reason, Stanines are slightly platykurtic, meaning that the tail, once it's been cut off like this, the tail is very short. Tails are not as long as a normal distribution. They're just cut off right here at 1 and cut off right here at 9. Legend has it that Stanines were invented with a very practical purpose in mind. That is, you could fit a whole Stanine number onto one column of a punch card. If you're not familiar with what these punch cards are, computer programs used to be stored on punch cards, data used to be stored on punch cards, and basically each column here represents a number. So if a hole is punched out here on the 5, the computer would read this first row as a 5, and then this one here that's punched out at 2, so it's a 5 and then a 2 and then a 5, and so forth. If each card represents a person, like let's say in the army, you could keep a whole bunch of data about that person on one card. And if you have to contain a lot of information about a person, you want to condense your measurement system such that you can get one number on each column. If you had some other kind of system, you might need 2 or 3 columns per bit of information. And if you want to, like have the soldier's IQ or something like that, you're only taking up one column. Now, there are people who dispute this, but it's entered legend and we'll just pretend it's true. That this is one of the reasons that Stanines was invented. Although the technical capacity of computers no longer requires things like Stanines, there's still good reason to have them. When you have measurement that is crude and you don't want to convey precision that you don't have, a Stanine is a good choice. Ray McCattell looked at Stanines and said, I could do one better. What he noticed was that you're using digits 1 through 9, and he said, what about 0? 0 is just as good and will still fit on the punch card, just one column. So he came up with something called the Sten, the standard 10. It only survives in Cattell's instruments, personality questionnaires like the 16PF. But since Cattell's measures are still used, I'm going to talk about the Sten. The Sten has a bit of a weird mean. It's 5.5, but the standard deviation is 2. The numbers are rounded to the nearest integer, and they range from 1 to 10. Does this look like a mistake, a 0? Well, no. In Cattell's system, a 0 actually represents a 10. So you're still using one digit, but anytime you see a 0, what it actually means is 10. Kind of weird, but that's the way it is. In modern applications of Stens, typically this 0 becomes an actual 10 to avoid the confusion. But just like the Stanine, each number in a Sten equals 1/2 a standard deviation. So if you score a 5, you're just slightly below the mean. But where? Not really sure. It's somewhere between a 0 and a negative 0.5. And again, the 1 and the 10 are cut off so that it represents from this line negative 2 all the way to negative infinity and positive 2 all the way to positive infinity. And Stens, therefore, are also slightly platykurtic. The next kind of scale is called the scaled score. Scaled scores have means of 10 and standard deviations of 3. Scaled scores are good when your z-scores are accurate to about 1/3 of a standard deviation. With scaled scores, the numbers are rounded to integers, and they range from 1 to 19. Occasionally, you'll see numbers from 0 all the way to 20, but typically the numbers are rounded and truncated such that they range from 1 to 19. 10 is the mean, and it represents a number that's somewhere between negative 1/6 of a standard deviation to positive 1/6 of a standard deviation. But for the sake of simplicity, we just say it's about the mean. IQ subtest scores, not IQ itself, but the subtest, the little parts of the IQ test, typically are not measured with a whole lot of precision, and so those scores are often communicated in scaled scores. So we have z-scores, mean of 0, standard deviation of 1. There are no range limits on a z-score, negative infinity to positive infinity. A Stanine has a mean of 5 and a standard deviation of 2. It ranges from 1 to 9, rounded to the nearest integer. Stens have a mean of 5.5, standard deviation of 2. They range from 1 to 10. Scaled scores, mean of 10, standard deviation of 3, and they range from 1 to 19. Now, a t-score is a good metric when your numbers are accurate to 1/10 of a standard deviation. So the standard deviation is 10, and 50 is a good number. It's one we're familiar with. 10 is a great number. And in this case, we don't put any limits on the t-score. It can go as low as you like and as high as you like, but in practice, it almost never gets below 0 or above 100. Many personality scales are given in the t-score metric. The normal curve equivalent is not typically seen in psychological measurement, but it's often included in educational measurement, and I include it here for the sake of completeness. Like the t-score, it has a mean of 50 and a standard deviation of what? 21.06? That's an ugly number. Well, yeah, that is an ugly number, but it makes something that's kind of cool possible. Normal curve equivalents range from 1 to 99, and that's kind of a cool thing. It looks like they're percentiles or something like that, and that's what they're designed to look like from 1 to 99, because people are familiar with percentages, and so we wanted some sort of standard score that looks like a percentage. It isn't a percentage, but it looks like one. It turns out that there are only 3 numbers on the normal curve equivalence scale in which the number and the percentile are equal. If you score a 1, that means you're in the bottom first percentile. If you score a 99, you're at the 99th percentile or higher. And if you score a 50, you're at the 50th percentile. But other than that, the numbers do not line up. Finally, we have the index score. It's also known as the standard score. What? Standard score? I thought that's what all of these were called. Yes, it's confusing but true. Index scores are so often used that when you say, I have a standard score, what you mean is the index score. Sometimes this metric is called the IQ metric because this is the metric that IQ scores are typically communicated in. They have a mean of 100 and a standard deviation of 15. An index score is good if you have a score that is accurate to 1/15th of a standard deviation. Like the t-score, there's no limit on the range. As a historical side note, for a while, there were actually 2 kinds of index scores, one with a mean of 15 and one with a mean of 16, and that kind of index score, the one with the 16 standard deviation, was almost exclusively associated with the Stanford-Binet IQ test. But now, even the Stanford-Binet uses the index score with a standard deviation of 15, and therefore there's no need to distinguish between the 2 kinds of index scores. There's now only one kind of index score. But the old Stanford-Binet index score did have a standard deviation of 16, and that was often pretty confusing. Are there different kinds of standard scores? Yes, there are more than just these, confusingly, but for psychological measurement, these are the main ones. In fact, some of these are more used than others. The z-score is often used. Scaled scores, t-scores, and index scores are the most common. Stanine, Stens, and normal curve equivalents you don't see very often. And therefore, this figure conveys pretty much all the information you would need. That is, on the x-axis we have several different kinds of measurements, and then here, of course, we have z-scores. So this point right here is 1 standard deviation below the mean. It corresponds to an index score of 85, a t-score of 40, a scaled score of 7, and not shown here, it's a percentile rank of about 16. Now notice something interesting. The percentile ranks represent what percent of people score below a certain number. So this 25 corresponds to about the bottom 25% of this distribution. So an 8 on the scaled score or a 90 on the index score represents the score that you would have to get better than 25% of the population. Now look at these percentile ranks. The distance from 0.1, that is 1 on 1,000 kind of score, to 1, the bottom percentile, is about the same as the distance from the bottom percentile to the bottom 5th percentile. And then the distance for 5 more is even shorter, and then the distance between the numbers gets very, very small till you get to 50, and then they start lengthening out again, and you get the same kind of thing that for each additional percentile at the top end, you have to go further and further out. This is why we don't communicate our results in percentile ranks. The distance between the numbers varies depending on where you are in the distribution. I wish this weren't true, because percentile ranks are much easier to understand than standard scores. But the fact is, the distance from 50 to the 51st percentile is very small, and the distance between the 98th percentile and the 99th percentile is much bigger. So percentile ranks don't have the same meaning everywhere in the scale, whereas standard scores do. A very important skill for assessment professionals to have is to convert from one kind of standard score to another. Because you get a lot of information in a lot of different kinds of metrics, it's useful to compare numbers that allegedly measure the same thing. So if you give 2 tests that measure, let's say, vocabulary ability, but one is in an index score metric and another is in a t-score metric, you would want to be able to compare those 2 scores. And one way to do it is to convert the t-score to an index score, or the index score to a t-score, and then compare them. So converting from one standard score to another is a 2-step process. The first step is to convert the old score, the one that you have that you want to convert, into a z-score. Then you convert the z-score to the new score. So here's the formula for a z-score, and I've transformed it a little bit. And then I have that z-score rearranged, but we've solved for x. So you can do the algebra yourself, but this is the z-score formula rearranged. What's different is that the subscripts are different from the old score to the new score. So let's take an example. Suppose I have a scaled score of 15 and I want to convert it to an index score. So I'm going to put this 15 right here, that's the old score, and then I need to subtract the old mean. Scaled scores, if we look back at our table, have a mean of 10, so I'm going to put that right there. So I've got 15 minus 10, that's 5, so I'll put right there. Now I need to divide by the old standard deviation. Scaled scores have a standard deviation of 3. Now, I could convert this into a decimal, but I happen to know that it's going to be easier if I don't. So what I'm going to do is I'm going to take that 5/3 and I'm going to plug it right here. So z equals 5/3. I'm going to plug it right here. Now I need to find the standard deviation of the new score that I want. The new one would be the index score. Index scores have a standard deviation of 15, so I've got that right there. 15 is 3 times 5, so I can take this 3 and that 3 and cross them out. And so what I'm left with is 5 times 5. 5 times 5, of course, is 25. And now I just add the new mean, the mean of 100. And so put that together, and my new score, the index score, is 125. So I started with a 15, I converted it into a 125. Let's try another example. Suppose I have an index score of 72, and I want to convert it to a t-score. So I'm going to take the 17 and I'm going to put it right here. Now, the mean of an index score is 100, so I put that right there. 72 minus 100 is negative 28. This negative is important, I can't forget it. The standard deviation of an index score is 15, so I put that right there. I could convert this into a decimal, but I'm going to leave it as a fraction. I'm going to take this z-score and I'm going to put it right there. Now I'm going to plug in the missing information. So the standard deviation of the new scores are t-scores. Standard deviation of t-scores is 10, so I put that right there. 10 and 15 share a multiple. If I'm doing this with a calculator, it doesn't really matter, but if I'm doing it in my head, this makes it a little easier. 10 is 5 times 2, and 15 is 5 times 3. They share a 5, so take out the 5s, and I've got 2 and 3. I'm going to multiply this 2 times the 28, so I've got 2 times 28 is 56, or that is negative 56, and then I'm going to divide by 3. In this case, I'm going to round with fractions, and it becomes negative 18 and 2/3. The mean of a t-score is 50. Now I'm going to add negative 18 and 2/3 to 50, and out will pop 31 and 1/3. Now this is the answer. I could convert it to a decimal, it's 0.3 repeating, but in practice, we round to the nearest integer, and so it's perfectly acceptable practice to round and just say it's 31. If you don't like my two-step process, you can combine the two steps into one big formula, like so. You take the old score that you're trying to transform, you subtract the old mean. Then you multiply this deviation by the standard deviation of the new metric divided by the standard deviation of the old metric, and then you add in the mean of the new metric, and out will pop your score. So if you want to do it in one step, you can do it, but I like my two-step process because it helps me remember that I'm converting to a z-score first, and then I'm converting a z-score to something else. So the z is sort of my leverage point, my linchpin, or my keystone, or whatever metaphor you want to, or whatever metaphor you'd like to give it, is that the z-score is a kind of a useful thing. Now I mentioned something about percentile ranks, and I want to talk about where that comes from. A cumulative distribution function is a function that tells us the proportion of a distribution that is less than or equal to a given number. If we want to get really fancy about it, we can do it like this. If f of x is the cumulative distribution function and little f of x is the probability density function, then the cumulative distribution function is the probability density function integrated up to a certain point, x. But that's a bit fancy, and we don't really need to understand this formula. We can understand it intuitively, like so. Here we have a normal curve. It's the probability density function. This is the cumulative distribution function of the normal curve. Now, each curve, each distribution has its own probability density function and its own cumulative distribution function. But what we have here is I've got a slider here that manipulates a certain number. This scale is a z-score scale. So if I say, well, I want to know what the cumulative distribution function is for a z-score of 1.27. So what happens is that I want to figure out what is the proportion of this probability density function that is less than 1.27. So this shaded region represents the dividing line between 1.27 and lower and 1.27 and above. What is the area under the curve that is shaded? And the answer comes from the cumulative distribution function. The coordinates of this dot represent the z-score, 1.27, and the cumulative distribution function, which is 0.898, meaning that almost 90% of the normal curve is below a z-score of 1.27. A z-score of -1 represents one standard deviation below the mean. How much of the normal curve is below a -1? Well, the proportion is almost 16%, or 15.9. So a cumulative distribution function just says what percent of that distribution is below a certain number. It's the area under the curve, basically. With the normal curve, the cumulative distribution function is known, and we can generate percentile ranks for each number. For index scores, there are just too many to memorize. But if you count by fives, you can memorize the percentiles that are associated with each of these numbers. It might seem like a lot, but I promise that if you do this, you'll be rewarded in many ways if you are an assessment professional. Memorizing this list has many, many benefits, and I promise that you will discover them. One of those benefits is that you'll be able to, on the spot, just generate what the percentile is for a given index score. Let's say you've got an index score of 122. Well, you might not know exactly what the percentile is, but it's somewhere between 91 and 95. Maybe it's a 93 or something like that. So you can come to rough estimates pretty quickly, even if they're not perfectly accurate. Another benefit is that it becomes easy to convert between scaled scores and index scores in your head if you memorize this table. So scaled scores range from 1 to 19. So basically, there are only 19 numbers to remember. If you do, when you're comparing scores, you can do it very quickly in your head. If you say, okay, a scale score of 15, that's a 125 in the index score metric, and you can compare numbers across batteries very, very quickly. You might not think that this is an important skill, but trust me, it is. When you're doing psychological assessments, you are bombarded with not a dozen numbers, but dozens of numbers, sometimes hundreds. And so you are just drowning in data. And if you can quickly understand what they mean and convert across in your head, you don't have to go through the laborious process of doing it by hand. If you just know what each score means, you know what the percentiles are, you know how they convert across, your interpretation can become very quick. Notice here that each scaled score is worth 5 index score points. That's a useful thing to remember. T-scores don't line up as nicely with index scores and scaled scores. They kind of have to go on their own. It's a good thing to memorize this list as well. Just a benchmark of 5 T-scores or half a standard deviation. Another thing that's useful to remember is that every 2 T-scores is worth 3 index score points. So let's say we have a T-score of 62. 60 is 1 standard deviation above the mean, corresponds to 115 on an index score, and 62 is 2 points above that. 2 points T-score is worth 3 index score, and so a 62 would correspond to a 118 on an index score. This is also useful to be able to convert between T-scores and index scores in your head. In my cognitive assessment class, I tell them that this table is optional, but I actually make them memorize this. They don't like me for a while, but it turns out that many students have come back to me and said, I'm really glad that you made me do this. I didn't like it at the time, but it really has made my life a lot easier.